Welcome to the last colloquium of the summer. I'm super excited to pass the baton on to Hanley, who's taking it for the next 9 months. Bill has been super kind enough to step in to give this talk this week because I had scheduled another speaker that is not visiting us. So he, on a very last minute notice, decided that it was a good idea to give a talk this week. So thank you very much. And a little background. So you all know him, and it's probably unnecessary, but he's been here for a while. So Bill is Ballard Professor of Engineering at the Thayer School of Engineering at Dartmouth College, and he has been an HAO affiliate scientist since 2010, and that's why you all know him so well. This time around, he's been in residence at HAO since March this year, and is returning to Dartmouth for the 2015-2016 classes just after Labor Day. So it's your last chance next week. His research interests include global geospace dynamics, with special interest in magnetosphere, ionosphere coupling, and including the production of outflows of ionospheric ions and precipitation of electrons that modify ionospheric conductance, and the effects of both on the solar wind magnetosphere-ionosphere interaction. So without further ado,
okay.
It's all yours.
Okay, thank you, Rebecca. I've actually, I think last time I gave an HAO colloquium, is this the colloquium or a seminar series? Colloquium. I look back, I can't remember, 2013 maybe, on a very actually early phase of this work. And it's ongoing. It's a problem that has a lot of nuances to it, and to really try and understand the physics is difficult to tease out. I mean, it's difficult to tease out in some of the simulation and modeling work I'm going to describe to you. It's even more difficult to tease out in observations and measurements. So I like to give an introduction to the problem I'm considering by giving you some insights from the observations that more or less pose the problem that we took on. And that's what I'll spend the first part of this talk addressing. And then a little bit about some of the previous work that has been done by others on this problem to get some insights. And then I'm going to launch into probably the last third to half of the talk on controlled experiments using global simulations, in particular using the LFM model, which is one of the NCAR models, HAO models that is used and is available on CCMC, for example. And then I will say something about the implications of the simulations for night-side reconnection, which kind of harks back to the title of the talk. Fast flows in Earth's plasma sheet, field line currents, power flows connecting the magnetosphere and ionosphere. And my main interest here is really how the magnetosphere and ionosphere shake hands to produce what we see in observations. And there's some interesting effects. Okay, just to make sure everybody's with me, geospace magnetic field geometry. The situation, this is going off the screen for some reason. It's almost like, well, I guess we're just going to have to live with that. We'll see. So what you see here, southward IMF, and this is a configuration. It should be familiar to most people, but we have magnetic reconnection opening flux tubes on the day side, go deep out into the solar wind where the field is frozen in. And so these field lines are drugged tailward and then eventually come back and they pinch off here. Reconnection occurs here, and then the flux tubes become closed again and then convect actually not through the Earth, but around the dusk side and the dawn side of the Earth to come back to the day side to maintain the so-called Dungy convection cycle. It's an idealization that is much more complicated than these simple pictures, but at least it gives you a framework for thinking about the magnetic field geometry. And back here, there's a neutral current sheet, and I'll say a little bit more about that in some of the observations. And it is a relatively high beta region. And in satellite data, when you're back here in the tail, and if you want to learn something about this process here, typically what observationalists will do is to limit the data set to relatively high beta so that they're sure they're in the neutral sheet. Because if you go up out of the neutral sheet in this region here, and of course this thing can flop up and down, you will be in a very low beta magnetic lobe region where the field strength's large and there's very little plasma. Okay, so one of the earliest studies that I would say Nagai and Mashita actually had the fortitude to claim that this effect was present in the data. There are others who had seen it earlier, Rumi Nakamura, for example, who saw it in AMPTY data in the early 90s and said, this is an instrumental effect. It's a sampling effect. It's not real. And Nagai and Mashita were very careful. And so they were looking at, and I'm missing the Geotail satellite data, and they were looking at Geotail satellite data here. And if you're earthward of the reconnection site, you expect an earthward exhaust flow headed earthward, and if you're tailward of that, you expect a tailward flow. And for more or less southward IMF conditions, the tailward exhaust would be carrying magnetic flux pointing southward, and the earthward exhaust would be carrying magnetic flux pointing northward. That's that little arrow there and there. And then there's some small diffusion region here, and the reconnection rate. Actually, it's almost independent of either the numerical physical model that is used, and in observations almost always turns out to be 0.1, the Alfvénic speed in the inflow region, times the magnetic field in the inflow region. It's a curious result, and I ask every time I hear about somebody talking about reconnection, can you explain to me why it's always found to be that way? And the best answer that people have come up with is that it's reconnection-like. That is, that the dissipation process that enables reconnection is not as important as the shocks that come off of the reconnection region and Pechek reconnection, and so it's basically a driven process. I think for spontaneous reconnection that is a subject of great study, this is not necessarily true, but for driven reconnection it is. Okay, so what Nakai and Mashita did was to, one, limit their study to relatively, and so you may not call this high beta, but compared to the beta in the lobes, it's high. So they limited their study to relatively high beta so that they could be sure they were in the neighborhood of the neutral sheet. And then there are three categories of data that they archived. And so the solid line in these figures down here is the sum of all events where they saw earthward exhaust flows going fast, 300 kilometers per second, that's relatively fast, with BZ northward, and tailward flows with BZ southward. So they felt that with this criteria here, they were either earthward or tailward of the neutral, of the reconnection line. Tailward only, the orange or whatever that color is, tailward only with BZ less than 0, and then black, tailward flows, fractional rate per observing hours. And so these are their histograms for those events. And to say a little bit more about those, let me just pull something up to give you a sense of the geometry here. This is actually from a simulation result, but it's mainly just diagrammatic here. And so these tailward flows here kind of tail out around 20 to 30 RE, and the earthward flows start to pick up. And so they inferred that, one, on average, the reconnection line's 22 to 30 RE. I think that's what appears in their abstract, for example. That's what you infer from this kind of histogram. And then another thing, and this is where I say they really had they were the first authors who had the fortitude to say there's an asymmetry in the tail that we don't understand. And they found that these fast flows in the neutral sheet were occurring with a greater probability in the pre-midnight region of the plasma sheet, the flows there. And so this occurred 1998. In 2002, Tai Fan and his undergraduate, Raj, did a study of wind perigee passes and also limited their study to fast flows and relatively high beta, and found a similar result. So 4 years later, other people are saying we see this. More recently, and there are actually a bunch of other studies looking at different types of diagnostics that confirm the same thing. But here you see 14 years of data from 3 different satellites put together, limiting the beta to relatively high, sunward flows only, and they calculated the duration in which they see flows that are in this range, 300 to 400 kilometers per second, normalized to all flows in the range from 0 to 1,000 kilometers per second, also correcting for the aberration of the motion of the Earth through the interplanetary medium. And you can see again that there's a pronounced asymmetry here favoring the fast flows in the pre-midnight sector. Okay, so many studies in the magnetosphere using satellites measurements. In the ionosphere, what do you expect to see? So Sergeyev was one of the first to note that if you have a flow, and these things were observed to be channels, so they have typically limited extent in the y direction across the tail, and they're headed earthward if you're on the earthward side of the reconnection line. So you imagine that you have this fast flow moving fast through the medium, which is moving more slowly, also in the general earthward direction. And that's going to polarize because there's a larger electric field in that region. The magnetic field may be a little different too, but there's a larger electric field in this region to accommodate that faster E cross B flow in the channel. And so it polarizes. And of course, the system wants to maintain charge neutrality to first approximation. So one way to alleviate the buildup of charges on either side of this channel is to send electrons up or down the field line to neutralize that charge accumulation. And those electrons are basically carrying field line currents, which are flowing down to the ionosphere and produce signatures in the ionosphere that Sergeyev said should look like this. And these are inertial currents as opposed to diamagnetic currents due to the motion of the fluid. And in fact, in the ionosphere, you do see signatures of these effects. They're often called poleward boundary intensifications because they're seen at the poleward boundary of the auroral oval. And sometimes streamers, which are an indication that they have a motion that's moving in the meridional direction, typically equatorward from the polar cap boundary. And not to spend a lot of time on this slide, but this is data taken from a meridian scanning photometer. It sits on the ground and it scans in the meridian up, back, forth, north-south in time. And also the Earth is rotating through that. So you see here 12 hours of sampling time. And these features that they see at higher latitudes beyond or near the poleward boundary of the auroral oval, these have come to be known as, or commonly called now, poleward boundary intensifications. They are thought to be associated, they're variable in time, as you can see here, and they're structured, and they're thought to be associated with these fast flows that are occurring in the plasma sheet. And imagine if you have a front on this fast flow moving earthward, it's going to be stroking the field lines as it moves, and it's going to be launching Alfvénic waves all the way through its transit down as it moves to Earth, and those Alfvénic waves are going to start impacting the ionosphere, and when those Alfvénic waves couple into the plasma and accelerate, they actually develop small-scale structure and accelerate electrons along the field line. That's what shows up as this auroral emission here, basically. At least that's the concept for why we see these things and what their connection is with these streams in the plasma sheet. Some statistics. These are a couple of histograms, a number of events, and so here, these poleward boundary intensifications as a function of magnetic local time. Midnight would be here. Again, at the ionospheric end of the flux tubes, there's also a pre-midnight persistence of the poleward boundary intensifications relative to over here at post-midnight. And then they tend to occur at relatively high latitudes, typically the auroral oval. The upward high latitude boundary of the auroral oval is considered to be somewhere between 70 and 74 degrees. Depends on magnetic activity and so on. And so that's where these things occur. And so another measurement, so these are inferred from optical emissions, okay, this histogram here. But now if you look at satellite data well above the ionosphere flying at 4 RE, the polar satellite or so, and start measuring electric and magnetic fields in situ, calculate the Poynting flux flowing along the magnetic field line, bandpass filter it to back out the Alfvénic component, and sample over a year of data, you get a distribution that looks something like this. So here are these poleward boundary, the Alfvénic signature of these poleward boundary intensifications well above where they're impacting the Earth's upper atmosphere. And of course, they couple energy into the electrons, relatively soft electrons, so-called broadband electron power that goes down and impacts the atmosphere as well. So these are all kind of different sides of the elephant that we're looking at here. And finally, let me just say something about precipitation. There are other types of things that can lead to this pre-post-midnight asymmetry. And in fact, it's been well known for decades that there's a pre-post-midnight asymmetry in the aurora. And one of the effects that's been known, and I'll come back to this in my summary, and I don't really have time to talk about it in detail. One of my PhD students finished up a dissertation this June. But what you see here in color, the background color here, is an inference of the precipitating electron power from the GUVI UVI instrument on the TIME satellite. So do an inversion algorithm to get some information about how much power is precipitating. And then from the Ampere satellite, which is this network of 66 iridium satellites, the APL group has developed algorithms to determine from the magnetic deflections that are measured on these 66 satellites what the distribution of field line current is flowing into the ionosphere. And so these contours here, the red contours are basically 2 sigma contours from the peak current, and red is for the currents that flow upward or out of the ionosphere. So it's the high latitude system over here and the low latitude system over here that flows out of the ionosphere. And then the gray ones are currents that flow into the ionosphere on either side, high latitude here and low latitude here. This region right here correlates very well, the precipitating power correlates very well with the upward field line current, and that's, I would say, fairly well known, that the so-called monoenergetic electron precipitation, and that's sort of code for electrons that are accelerated by field line potential drops that develop above the about 1 Earth radius altitude above the Earth's ionosphere. They develop because the field line current becomes charge carrier starved in that region. And in order to maintain current continuity, parallel electric fields develop, and you can carry a lot more current if you just boost up the velocity on the electron. So that's why that's occurred there. And that's been studied since the, I would say, late 70s through the 80s. It's fairly well known. Over here, this upward field line current is weaker statistically than this one over here. And the electron precipitation that's associated with it has relatively weak potential drops, and it's mainly the diffuse precipitation, which is associated with scattering in the loss cone at high altitude, and then precipitating relatively energetic electrons, 10, 20, even 100 kilovolt electrons into the atmosphere that produces that auroral emission. Okay, so I show this just to point out that there are other types of asymmetries here that may not be due to these fast flow channels and the reconnection rate that are due to other effects associated with the magnetosphere-ionosphere interaction and are interesting to study as well. Okay, so now let's go away from actual observations and look at what some empirical models tell us about the state of the ionosphere in these regions. And I'm going to try to put these things together for you as we go along here. So the well-loved Weimer empirical model for high-latitude convection, this model was developed from thousands of Dynamics Explorer 2 orbits at relatively low altitude, 800 kilometers or so. And they measured the electric field on that satellite and the magnetic field on that satellite. And so Weimer developed a model, and it's improved over time, that allows you, and you can go to CCMC actually and run this model. And so you can put in whatever actually you can put in the day, and it will give you a pattern like this for the time of day and in a particular year. If you're interested in an event, I put in BZ minus 5 nanotesla, kind of a nominal value for the interplanetary magnetic field. Creates activity in the magnetosphere, but it's not like a storm. No asymmetry in the interplanetary medium in this model, although statistically these are 45-degree bins in IMF, so there's clearly some other effects that have to be contended with in an empirical model like this. Nominal solar wind velocity, no Vy or Vz, and a kind of a nominal density of 8 particles per cc at 1 AU. And so this is what you get out of the Weimer model. And I'd like to point out a couple of features here that have been out there for quite a while. And the question is, what causes them? So one, if you draw, so these are actually equipotential contours, and it's practically a theorem. You can show that equipotential contours in the ionosphere are equivalent to streamlines of the E cross B velocity there, if the electric field is potential. So these equipotential contours are equivalent to streamlines, and the flow is tailward over the polar cap and then recirculates and comes back, goes to the day side, and so on. So this is the ionospheric signature of the Dungy convection cycle. And you can identify a potential minimum and a potential maximum, and if you draw a line between those two, you notice that it doesn't go straight across, even though the solar wind conditions supposedly don't have any asymmetry in them. There's some rotation of this pattern. And furthermore, you can see clearly in these contours here, which are color-coded, there's more magnetic flux circulating in the dust cell than the dawn cell. And that obviously must have some implications out in the magnetosphere, because these field lines are connected between the equatorial magnetosphere and the ionosphere. So we have more flux circulating on the dust than the dawn side. And no dipole tilt would be something like equinox. You can run, and I won't spend a lot of time here, but you can run Weimer for all different conditions, and you see. So across the top, I put in dipole tilt, which would reflect different seasons, equinox, and I kind of forget what minus is. I think minus is summer, and positive tilt, this is where the dipole's tilting away or from the sun. Summer, winter, and then here I kept 0 dipole tilt and just cranked up the IMF, so -2, -5, -10 nanotesla to see what happens. And across all these values here, you find this persistent feature. There's always a rotation of the pattern regardless. And there's always a more flux circulating in the dust cell than the dawn cell, fairly persistent. And these are a couple of figures directly out of Weimer's 2005 paper. And he varies the IMF clock angle all the way from 0 to 360 in each of these plots, winter, equinox, and summer. And this is the total, so delta PC means the difference between phi dawn and phi dusk, which would be the sum of the magnitudes of the two. And you see, in almost all cases, there's more potential in the dust cell than the dawn cell, more magnetic flux circulating there than in the dawn cell, almost always. Okay, now let me start to talk about some modeling work. So there was some work done in 1978 by Atkinson and Hutchison back in the days when we were doing semi-analytical models and maybe calculating Bessel functions and that kind of thing rather than just doing full up, finite difference grid simulations. And they started to understand some of the effects, this rotation effect, as being due to the EUV conductance in the ionosphere. So EUV is produced by photoionization of the dayside ionosphere. It's obviously going to be highest ionization state on the day side, and then as you go over the polar cap and get into the night side, that ionization concentration dies out. And so there's a gradient in the conductance in both Hall and Pedersen conductance from day side to night side here. What was realized by Atkinson and Hutchinson, although Ridley et al. Using the BATS-RS global simulation model put in a Pedersen conductance here. But what you find is that this Hall conductance gradient actually is responsible for this rotation that you see down here. Remember, this is a simulation, doesn't include any auroral precipitation and conductivity due to that, so it's an idealization. But just to see what effect EUV conductance has. And you see a rotation here, and you also see an asymmetry in the dusk and dawn flux circulation or potentials as well. If you made the Pedersen conductance absolutely uniform, you would still see this effect. If you made the Hall conductance uniform and allowed the gradient in the Pedersen conductance, you wouldn't see this effect. It's about the Hall conductance, and I'll give you some insights into that shortly. So what does that say? Well, this rotation, and I'll give you some insights into why this seems to be the case, but it seems that the ionosphere polarizes. So we have a gradient in the Hall conductance here. The Hall current is basically the electric field times the Hall conductance crossed in, or the magnetic field direction crossed into it. And so there's a divergence in the Hall currents, and the Hall currents basically flow in the same direction as the convection. Actually, they flow anti-parallel to the convection. And so this is the divergence in the Hall current. And what happens is that the system rotates and polarizes so as to maintain the Hall divergence essentially zero. And that's not intuitive at all, but that's what seems to happen in the system. Okay, so field line current closure in the ionosphere. This is a nice picture which was developed here at NCAR. Wonderful graphics. And just to orient you here, so these are the anti-streamlines that I showed in the Weimer plots earlier. And the Hall currents, because the Hall currents are basically B hat crossed into E if you ignore the neutral wind component, they're basically flowing anti-parallel to the convection. So the convection goes day side to night side, circulates around this way on the dusk side and around this way on the dawn side, and Hall currents run just anti-parallel to that. So if you have any gradient in the Hall conductance along that path, you would expect a divergence in the Hall current if that were the case. And of course, auroral precipitation will do that, and EUV ionization will also do that. The Pedersen currents flow in the direction of the electric field, sigma PE, and so they actually flow across these convection streamlines that you see here. Okay, now to give some insights into this polarization business and what happens. So I could do this for the EUV gradient, but I want to talk more about the auroral band, and so I'll work this out graphically for you. And so this is a simple 1D picture. Imagine midnight's over here and noon is up here. So take that polar cap view and just take a slice between noon and midnight. And so if we have precipitation that's producing an enhanced conductivity here on the night side, and similarly on the day side, although that precipitation would tend to be ameliorated, or let's say masked, by the strong EUV ionization component, which is not shown in this picture. Okay, so suppose that we have, in this picture here, we have an electric field which points upward in this plane here. And so the and if we're in the northern hemisphere, the magnetic field is into the plane of the paper. So E cross B is from right to left in this picture. And so that's the flow over the polar cap from noon to midnight in this simple picture. And the Pedersen currents are going to flow in the direction of the electric field. So the Pedersen currents flow across the polar cap this way, and the Hall currents flow anti-parallel to the E cross B velocity because they have this form here. And Same situation here. Suppose that the conductivities are uniform in each of these 5 bands, but the same, for simplicity, the same low value of the conductivities in the green region and the blue region, a high conductivity value. So as the Pedersen current, which flows, remember, anti-parallel to the streamlines, as it flows across this gradient, there's going to be a divergence in the Pedersen current because there's a divergence in the conductance, or a gradient in the conductance there. So charge builds up at these boundaries, of these boundaries here. And there are 2 ways to alleviate that charge. I mean, that becomes a crisis for the system, because if it keeps pouring current into the system, or the keeps driving currents, it's going to charge up greater and greater and greater, and something has to happen. Okay. So one way to alleviate the situation is to, here we have positive charge, so let's just bring electrons in from the magnetosphere and neutralize it, and let's send these electrons out and get rid of that excess charge that appears here. And so remember, electrons flow in the direction opposite to the field line current, so you can have field line currents that neutralize those charge buildup, and everything's okay. No longer any divergence in the total current. Still a divergence in the Hall current, but that divergence in Hall current goes into field line current to maintain total current continuity. Now there's another way to do it. That's not the only way to do it. So the other way to do it is to take this polarization. So mind you, originally we have an electric field which points upward, and positive charge here and negative charge here is going to produce an electric field which points in this band anyway. It's going to point from right to left in the band. And so that's going to cause a rotation in the electric field, a rotation in the Pedersen and Hall currents. And if that polarization is just right, it can shut off the divergence in the Hall current, basically. In other words, it can make, if this polarizes differently than this region here, then it can make the flow of Hall current continuous across here. It just depends on how much you rotate the Hall currents. And so it's the component of the Hall current here in the horizontal direction. And if it matches the component of the Hall current here in the horizontal direction, we don't have divergence in Hall current anymore. So polarization can do the same thing for you. And for reasons that are not entirely clear, so there's more problem to do out here, the magnetosphere-ionosphere interaction prefers this situation here. So, and I think, I'll just say, I think, and this is a conjecture, but I think the reason is that the magnetosphere is acting like a current source. It says, I can give so much current. Ionosphere, if you need more, too bad, deal with it. And so it polarizes, and so maintains the same current flowing through the system. Okay, so I've talked about the ionosphere here. Now let's go out and look at some results from modeling in the magnetosphere and see how these effects are coupled into the magnetosphere. So the global simulation model, this is actually, it can be run in the multi-fluid mode, and we've done some studies, and Mike Wiltberger's been actually started some of this work here at HAO. Using the multi-fluid LFM simulation. So for each ion species, and I think 2 of my former graduate students hold the record for the number of fluids, and so they've like put something like 12 fluids into this thing to see what they do with different characteristics. But so there's a different equation. There's an equation of mass continuity, momentum continuity, and energy, and for each species in this model, and then Faraday induction here. All species basically move at the E cross B velocity, but their field line velocity can be different in this model, and the perpendicular velocities have to adjust to accommodate those potential differences. If you sum over all ion species, you basically get down to one fluid, which is what I'm going to talk about. I'm going to talk about results from one fluid, not the multi-fluid. I like to say that this is, in one sense, it could be run, you could think of this almost, the one fluid as ideal MHD, practically. So how do you turn the equations of one fluid MHD into a magnetosphere? You need 3 things. You need a point dipole to represent the geomagnetic field, and you could soup that up if you wanted to and put in the South Atlantic anomaly and all these other things. you need some effect of the ionosphere, the fact that you have this conducting layer at the feet of the field lines, and they got to drag through that conducting layer, and that's going to change things. And you need something to represent the solar wind blowing past this thing. So you put those three things into ideal MHD, voila, a magnetosphere pops out at you. And I think John Lyon, when he actually started developing this code in the late 70s, early 80s, was quite surprised that MHD had no reason to work as well as it did to produce a magnetosphere that was anywhere near realistic. And so it worked surprisingly well. Okay, let me return to the case where there is only an EUV conductance in the ionosphere, and here it's only Hall. So this is a tiny figure, but this little Earth here is polar view is supposed to represent high Hall conductance here, linear gradient going from day side to night side. So it's like those previous pictures that I showed in the BATS-RS simulation. And now we're looking at the magnetosphere. Ridley showed us pictures of the ionosphere. Now we're looking at the magnetosphere here. And this is for a case of due south IMF after this preconditioning period to kind of populate the magnetosphere with fluid and lose some memory of the initial conditions. And then it's a 1 hour average at the end of this period. And this is for 4 nanotesla. So due south, there's no asymmetry in the solar wind in this simulation. There's no dipole tilt or anything like that. Dipole's pointing due north out of the paper here. And so you see an asymmetry here, just due to the EUV conductance. And if you march along this X line, this is the BZ equals 0 contour, the average BZ equals 0 contour, and calculate the electric field along there. On the day side, you see that it's fairly symmetric. But on the night side, it's quite asymmetric. There's more, the reconnection rate on the night side over here is greater than it is over here. And that's due to that Hall conductance gradient that we saw in the earlier work. And another curious result, and I don't think we know quite what to make out of this yet, but if you take the streamlines from the ionosphere that you see in these simulations and map the electric field as if the field lines were equipotentials back into the equatorial magnetosphere, then these are the streamlines that you see here where these red ones are all the ones that are in the dawn cell circulating, and these over here are in the dusk cell circulating. You would get a similar pattern if you just try to develop streamlines from this average MHD state, 1 hour average MHD state. You'd see a similar picture. But the curious thing here is that some of the flows and the flux that emerges from night side reconnection here goes around and actually reconnects on the day side in the pre-noon sector. We're not quite sure what that means or whether it's even important in the overall dynamics of the system. But things are not nice and symmetric like, these cartoons we have in our mind. Okay, so we've done a lot of work at Dartmouth, Ben Zhang in particular, trying to develop a much more sophisticated precipitation algorithm that we can embed. So this is a very non-ideal MHD effect that we use the MHD variables to develop this model to characterize and this is the monoenergetic precipitation, so this is one that's produced by a field line potential drop, although I need to back off here and say one thing about how this is done in the simulation. These simulations, this is historical. We're doing it differently now. But historically, a field line potential drop was calculated from this relationship was known since the 1973, some people call it the Knight relationship. And it's been well verified observationally that the field line potential drop is proportional to the field line current, particularly in the upward current channel. Downward current channel, it's a little different. And so you can calculate the field line potential drop, and you can calculate the effect that would have on electrons, accelerating them down, increasing their flux, changing the ionization state, on and on and on. And so that's done in this algorithm, but the field line potential drop is not taken into account in mapping the ionospheric potential up into the magnetosphere. If you have a field line potential drop, the potential can't be the same at the 2 points. So it's a little bit of a kludge in the model. And it has, if you put that back in, it does have some interesting effects, but it's not, the potential mapping is not included here. And so we go through, we calculate based on MHD parameters using proxies for electron, MHD variables for electron, use that to determine an effective resistivity, use it to determine the field line potential drop, use that in these relations, theoretical formulas which have been known for some time. Calculate the number and energy flux, put that in an empirical model or in the CMIT, the model that couples TiGCM to LFM, ingest it directly into the ionization model in TiGCM. Calculate Pedersen and Hall conductances, go back to the equation for ionospheric electrodynamics that I mentioned earlier, and I should say added to this is the EUV and the broadband contribution. I'm just showing here how an algorithm works like this. And then once the potential is calculated, use it as a boundary condition in the MHD solver, and then just keep going around this loop. So that's basically what happens. Okay, so what do we see? So there are three different cases here. So this case here has uniform conductance. So the color here is Hall conductance. The contours are equipotentials or equivalently streamlines. The white line here is actually, you kind of have to look at the two of these things together. This is the BZ equals 0 contour in the equatorial plane. This is a 1 hour average for IMF going through 2 hours south, 2 hours north, and then 4 hours south, and then compute a 1 hour average at the very end. This is very noisy. Even though the solar wind is dead steady, this system is churning all the time. And so we compute averages to get make some sense out of what we're seeing. So this is a BZ equals 0 contour here. If we map that along field lines down to the ionosphere, it looks like this in each of these plots. And then this point here is where the zero potential contour in the ionosphere crosses that mapped X line, and similarly on the day side. And so those points are then projected back up to see where they lie here. And then the potential minimum and maximum are mapped out here. So there's a lot of information in this plot, but the main takeaway here is that for uniform Hall conductance, the night side reconnections more or less, I wouldn't call it uniform, but it's not asymmetric dawn-dusk or pre-midnight, post-midnight. It's about the same on both sides. And there's not much of a rotation in the convection pattern in the ionosphere at all. Now, if we put in the full EUV and precipitation model, so we call this a causal empirical conductance model, into the simulation, now we see this asymmetry, faster exhaust flows coming out in the pre-midnight region than the post-midnight region. And we also see these are the values of the potential minimum and maximum. And so we see an asymmetry, more flux circulating in the dusk side than the dawn side in this case. And then if we go in and we actually do something which is not physical, but at least it allows you to test your ideas, go in and actually dig a hole in the conductance. So that's why this is blue here. And so it's a low conductance band around here, higher conductance in the polar cap and low conductance out here. And what you see is, and so you could think of an idealized situation like this where you just have a band of high conductance here, and it would produce an effect something like what you see here. But it moves the asymmetry to the other side in the magnetotail and causes a rotation in the opposite direction. Okay, so you get the idea that you're kind of getting at the problem here. You're getting a sense of what's going, even though the physics of it all is still not entirely clear. Okay, so what we did was we walked around this reconnection line and calculated the electric field on this reconnection line, and then integrated it to get the electric potential along that line. And so basically that's just an illustration of what's being done there. Basically calculate E.dl marching along that line starting at noon and go all the way around and come back. Yeah. So the asymmetry in the reconnection, um, EUV has a huge effect. As you saw, if I just go back to this case right here, this only has EUV. And so you can see that it's actually having a very significant effect on the reconnection rate on that side. But the Hall, so there's a gradient. In other words, in this band here, just going back to those simple 1D pictures I showed, remember the Hall currents are flowing through this region here. They're flowing sunward, and here they're flowing sunward, and so they're flowing right through this gradient in the Hall conductance. So you know that there's going to be a divergence in the Hall conductance there. And that's why the pattern rotates, because it's polarizing. So now we have an orthogonal component to the original electric field. The original electric field is just pointing from dawn to dusk here. And now we add a meridional component, causes the whole pattern to rotate. Okay? She's not supposed to ask questions in public like that. But okay, so integrating along the reconnection line, we see something, for these three cases, we see something like this. So for the uniform case, the minimum and the maximum potential on dawn and dusk is about the same. It's not the same for the causal or the depleted conductance, auroral conductance case. And some of the things that you conclude from this is that, one, the reconnection rate is larger on the night side than the day side. If this is the potential, then it's steeper on the night side than the day side, so reconnection rate's larger there. The dusk side potential is larger than the dawn side potential in magnitude, as we see in empirical models and in observations. And now, if we try to get a handle on the actual reconnection rate numerically, and so computing an average over the reconnection line in this red region here and this yellow region here, and same here. So for the causal case, the average reconnection rate, average 1 hour pre-midnight, is about 0.96 millivolts per meter versus 0.83, and it reverses in the depleted case. So the reconnection rate is larger, and that's why the fast flows the flows are faster. Those exhaust flows coming out of the reconnection, because you're reconnecting more magnetic flux, reconnection rate's higher. More magnetic energy is being converted into plasma energy, and that's exhausting out to maintain flux conservation. Okay, I have two more slides here, and then I'll summarize. And now we get kind of complicated, and I just want to give you a sense of where we're going with this. So we're trying to get at the current generators and what's the source of field line currents that are flowing and that are communicating between the ionosphere and magnetosphere in this simulation. So this is the same basic IMF configuration, but this is the same code run at twice higher resolution, so there's a lot more structure in this code. And I think Mike Wiltberger's talked about some of the interesting dynamic effects that are seen in the Magnetotail here. And so here in red, red is the component of the current flowing from anti-sunward to sunward. So it's just the component left to right. Red is left to right in this plot. This is a plot of the field line current taken a half RE out of the equatorial plane. Field line current goes away from the equatorial plane into each hemisphere. So if you try to calculate exactly in the equatorial plane, you get almost zero. So you have to go a little bit above or below to get a non-zero value. And then this plot here, color-coded again, is the field line current now at the ionospheric level, streamlines, and the night side reconnection line mapped down into this region here. Notice the difference in the magnitudes, nanoamps per versus microamps, due to basically field line current divided by magnetic field intensity is conserved to first approximation. Magnetic field's much weaker out here than it is down here. And for those of you who don't live in geospace like some of us, early on, Ejima Patemer identified just morphologically without any physics, saying, okay, we see statistically a high latitude current system out of the ionosphere on dusk into the ionosphere on dawn. We'll call that the region 1 current system. And then at lower latitudes, region 2 current systems with the opposite polarity. And so what we see here, we think, we have more work to confirm some of these things, but it appears that there's a closure. So there are two ways in which, well, there are more than two, but two simple ways in which you can close these currents in the ionosphere. Blue is out and red is in, so you could have a current coming in, flowing across the field, and then out. That would be a Pedersen current. Or you can close the current, you can have it coming in here, flow across the polar cap. So R1 can close to R1 on each side, but R1 can also close into R2. And in the ionosphere, in the equatorial magnetosphere Plasmasheet, these regions here, so this is a JX here flowing from larger distances to smaller distances here. So that would have to be fed by a current flowing into the Plasmasheet here. That's the R1 coming out here. And then out of the Plasmasheet into the ionosphere, that's the R2 here. So we think these are the R1, R2 closure current systems that are feeding closure here, or supporting it, I should say. And those are almost certainly due to diamagnetic currents in the Plasmasheet, because there's fairly strong pressure gradients in those regions. And then there's a gradient in the JX component that's shown in this dotted line here. And you can associate that with various field line current features, smaller scale features that you see here that have these projections down in the ionosphere, and this kind of turning of the convection pattern, this knee in the convection pattern you see here, is associated with polarization of the electric field in the ionosphere and its effects in the Plasmasheet. It's kind of complicated to put these two things together for all of us. And then you can look at, okay, so what's supporting that divergence, that JX there, and its divergence, and there's an X variation in the Y component of velocity here. And so I actually don't, here's the Y component of velocity here, so a dVy dx occurring right here. And the divergence of that then goes into the field line currents. So let me summarize with a few key points to leave you with. So one, the effects of meridional gradients in ionospheric Hall conductance. One, the polar cap to night side auroral zone gradient. So that's the band on the night side. And there's a gradient in which the conductance is higher in the auroral zone than it is in the polar cap. And it's caused by electron precipitation ionizing the upper atmosphere and producing an enhanced ionosphere there. That effect tends to rotate polar convection clockwise and gives rise to a westward flow. And that was suggested from some semi-analytic studies early on by Yasuhiro et al. And Barbosa. And leads to an enhanced reconnection rate and fast flows in the pre-midnight sector. The day side to night side gradient, due to the EUV ionization, rotates the polar convection counterclockwise. So it counteracts the direction of rotation due to the auroral gradient. And it also enhances the dust side reconnection potential. And it's a bigger effect there, and is largely the reason why there's, or I should say, the effect that's producing this higher flux circulation in the dust side than the dawn side. And then there's this Cowling polarization effect, which is kind of interesting. So you have this, which I talked about in the last slides there. You have a meridional electric field, which is due to that polarization. And that's closed by a meridional current system in the Plasmasheet. And that has actually been inferred in satellite data. It's very complicated to get at that because you have to do it statistically. But something that I was not familiar with until we did this paper that we submitted to Science, and one of the referees came back and said, you know, it's reassuring that you did this because it's already been seen in data. You know, the referee story. And it was nice to see that, and I had not been familiar with a current system that flows in kind of the axial tail current systems that are actually seen in the plasma sheet, but they're there. And then the last couple of things, well, the last thing I'd like to leave you with, and I said this earlier, but the provisional divergence in the Hall current at Hall conductance gradients appears to be accommodated primarily by polarization rather than diversion into field line currents. And that seems to be telling us that the plasma sheet dynamo is acting as a current source, not a voltage source. The day side may be more of a voltage source, the night side seems to be more of a current source. And something I did not talk about but alluded to, Shenzi's, one of my PhD students who finished up recently, looking at the effects of field line potential drops. And this is kind of interesting, and we need to do some more work to really understand what's going on here. But when you have, in that upward current channel on the dust side, field line potential drops developing there, those field line potential drops have an ohmic dissipation associated with them, and there's more dissipation on that side than on the dawn side, and that has to be powered in some way. And so that there are additional power flows coming in from the plasma sheet to power that ohmic dissipation. The reconnection rate is higher to accommodate that higher power flow from the plasma sheet. And the way that the system appears to accommodate that, looking at some of the simulation results from Shen, is that in the pre-midnight sector, in those simulations, the X-line moves a little bit closer to Earth than on the post-midnight sector. And if you think about what's going on there, the magnetic field strength intensifies as you go closer to Earth, in the lobes in particular. So the inflow region to the X-line has higher magnetic flux, and therefore you can convert more magnetic flux. If you move the X-line closer to Earth, you can convert more magnetic flux into fluid energy and accommodate the enhanced power associated with the motional dynamos that result from that effect. That's what we think is happening. And so I'll stop there. If you have any questions, thank you. Michael has his hand up.
Mentioning that we're presenting the calculations in 1 hour average.
Yes.
Because there is a lot of fluctuations going on all the time.
Yes.
Now, the simulations are fully 3D.
Fully 3D, time dependent.
So, and here comes my simple. So, we have the Earth rotating around the Sun and rotating. We have the day and night issue, but at the same time, this dipolar magnetic field that you pointed is slightly tilted, of course, against rotational.
Right.
So, and then, I mean, if I want to sort of really strict about it, even the stuff that comes in with the solar wind has a certain tilt because of the sector structure of the interplanetary field. So, is it that just these geometric factors create this kind of volatility?
I mean, that's an obvious place to start to look, but you may have come in after I showed this one plot, but there's one data set in which they've taken 3 satellites and data from them over a period of 14 years and computed average statistical characteristics. And you would think, although there could be biases in the data set, but you would think that sector structure, dipole tilt, IMF BY, because in any given data set you can't have pure southward IMF. Those effects, you would have as much IMF BY east as west, as much dipole tilt one way or the other, and so on. And so I think if you use statistics over a long period of time, you would expect those asymmetries, which would be the solar wind can clearly introduce asymmetries, would be washed out. But as I said, there may still be some biases in their data, but they did the best they could to try and eliminate them. And of course, in the simulations, we don't have to contend with that. We can go to the idealized situation where there's absolutely no asymmetry in the solar wind at all. It's all coming from the ionosphere.
Maybe something similar to this in the ionosphere, will spread out bubbles that form the simulation and just have Harrison curves there. Activity, the fall, the bubbles come up nice and symmetric. The fall comes out and towards on the crystal.
Maybe a related effect. Yeah.
So the question is then how are the currents flows in?
Yeah. Yeah, right. I wouldn't be surprised if there's a similar effect because those things are moving, so there's some E cross B motion associated with them. So, yeah, interesting. Dolores.
Can you go back to that slide where you showed the cell and two
Oh, the Tien Lu's, this one.
Yeah. Any ideas about what
Well, we're scratching our head on this. The thing that's curious about this is that the red line is dayside reconnection. There's essentially no asymmetry on it. The dayside reconnection is dominated by that strong solar wind, the shock solar wind coming in and pushing flux up against the magnetopause. And so, the system there more or less has to accommodate that and the symmetry that's present in the shock solar wind coming against it. Internal to the magnetosphere, it doesn't have to be that way. All that's required is that on average, the flux reconnected on the day side balances what's reconnected and coming back from the night side. But I know you look at that. I mean, we looked at this too and said, okay, so that's interesting. What does it mean? Does it even matter? But remember now, this is an extreme case. This is pure EUV. Now you put the auroral in there and it moderates this a little bit, but it still happens in the.
something that you can preferential for the summer?
For the what?
For the summer.
Probably for the summer, right? Yeah. I mean, if you were Gerhard Herendell, you'd go, wow, I can release an explosion from a satellite in space, barium ions, and follow them and see where they go. That's. Yeah, Gerhard likes to say that barium cloud is the largest man-made object ever. Yeah, this was on the empty satellite. They released the barium ions in the into the magnetosphere. It's just right. Yeah. Yeah.
So, if I may, another one. Said that the magnetic field is essentially protecting the atmosphere from being constantly depleted by
Yeah.
planets that don't have a magnetic field, therefore strict
Atmosphere.
The atmosphere,
yeah.
or is the all the big connections pushing, because that's what we see in the Aurora, or is basically more kind of sucked back in?
There's during intense storms, there's clearly loss of both oxygen and primarily oxygen and protons, and the way that they come out mainly is through, well, I've got a different plot here, but let me just go back. They're basically coming up in this dayside cusp region here and over the polar cap is polar wind. And they're coming out and they're flowing, a lot of them, and particularly the not very energetic ones, are coming out on open field lines and flowing out the tail. And that's seen by the cluster spacecraft, and particularly, they don't have mass discrimination on the measurement technique they're using there, but they see a lot of ions going out. And then during storms, those fluxes coming up, I mean, basically during storms, electromagnetic power goes into the atmosphere and ionosphere, and it reacts by getting exercised and sending mass up. But some of it also gets lost. Some of the flow out through the magnetopause here also gets lost, and it comes back and goes up over the polar cap, and then you get plasmoids ejected down tail. So there are a variety of different ways in which there are losses. However, if you ask over the sort of the geologic age of the solar system, how important is that effect? It's minuscule. And the reason is that almost all of the oxygen, for example, is in the oceans, in the solid earth. And so what's in the atmosphere and what comes out, what's estimated to come out through these processes is a relatively weak flux on the time scale of 4 billion years, for example. So it's an interesting question. It'd be great if it were something more to worry about, then we'd have a lot more to talk about with our congressmen and so on.
Data's coming in on other systems, and where you might have sort of a really hyperactive star, and then the question is, does that change the stability of the atmosphere?
Yeah, right. It's conceivable, and I suppose one could estimate that, say, what kind of fluxes would you have to have leaking in order to seriously deplete, particularly if there was no ocean or anything, and it's mainly a solid gas interface. Okay, thank you all.